Hi, welcome back. We continue with finite element method. We go to strain energy. We consider one bar here subjected to P. P is external load. So this P will provide strain energy. The strain energy U is an internal work or energy stored in elastic material due to external load. So this is definition of strain energy. So if the bar elongate or displace, so the energy from the external load will store in the material. So the energy stored in the material due to external load is called strain energy. So we consider one element here of distance, small distance, delta x. The stress is sigma x and sigma x at other side. So at this point, the displacement is ux, and other side of this element, the displacement is u, function of x plus delta x. From last class, the displacement ux, the displacement u is a function of position. Okay, so position is x. Here the position is x, so the displacement is ux, and at this point, the displacement is u, and the position is x plus delta x. We define du. So du is incremental of strain energy, or the strain energy. The strain energy in the bar of distance delta x. So this is du. Du is force time distance, or incremental displacement. So incremental displacement here is u x plus delta x minus ux. Okay, so this is incremental displacement. What mean by incremental displacement is ux plus delta x minus ux. So du now is force. Force is sigma x times a. Okay, the stress time area of this element, cross-sectional area of this element, times du. So incremental displacement is du, or this. So du is this, u at x plus delta x minus u at x. So this is du. So sigma x, this is equal to sigma x a times du dx. So this is from Taylor series. from Taylor series, we can say that U x plus delta x equal to U x plus delta x du per dx plus delta x square per 2 factorial times second derivative of u with respect to x and plus and so on. So this is Taylor series. So this is Taylor series. So from here, u x plus delta x minus ux. So this is delta x du per dx. We ignore this term. So we ignore this term. So we found that this. So this is from Taylor series. So du here. Du here is represented by this term. Okay, du. So this is equal to delta x times du per dx. So this is delta x times du per dx. Okay. So from here, sigma, this is equal to sigma x times a. From last class or last video, the strain x. Okay, we define strain x, or we have derived that the strain x is a differentiate of displacement. So this is derivative of displacement. So this is strain. Yeah. So this is strain times dx. So this is equal to sigma x strain a dx. Okay. So a dx represent the volume. So this is dv, yeah, or a dx. So therefore, we need to integrate. If we want to find u, because this is du, so du is just for one small element. So for all element here, or for this structure or this bar, so the total u, we need to integrate this term. So the integration of this term, we integrate this term, so this is become u. U is integration of sigma x times strain times a dx. So a dx is equal to dv. Okay, so basically this is the formula for strain energy for one bar. Okay, we learn the concept of virtual work. The total virtual work we denote it as VW, done by a set of real forces in equilibrium going through a set of corresponding virtual displacement is equal to 0. So from this definition, or from this idea, virtual, so delta, we use delta to indicate virtual work. Okay, W is stand for work. So virtual work is equal to 0. So if this is satisfied, the virtual work is equal to 0, then the structure is in equilibrium. In general, there is both internal and external virtual work, and the sum is 0. So the virtual work composed of virtual work external plus virtual work internal. So the sum is equal to 0. This comes from this, and virtual work external plus virtual work internal is virtual work. So in mechanics class, we learned that virtual work internal is minus virtual strain energy. Okay, so if we substitute here, virtual work internal equal to minus virtual strain energy. So virtual work external, so we substitute here, so minus virtual U, U represent the strain energy, so equal to 0. So meaning that from this equation we get this. So virtual work external is equal to virtual strain energy. So this is principle of virtual work, and if this is true, so the structure is in equilibrium. Okay, so for proof, you can see in my PDF file. So see in virtual work principle, this is PDF file. Okay, so we consider a virtual strain energy. Okay, so this is virtual strain energy. We consider one element of distance, dx, dy, and dz. So this is axis, x, y, and z. A stress we apply, or this element is subjected to stress sigma x and sigma x at this side. So this is we call real stress. So we have no virtual here. This is real stress. Differential force real is just sigma x times area. Okay, so area of this side is dy times dz. So sigma x times dy times dz represent differential force, and it is real. This element, we consider this element is deformed in virtual. Okay, so virtual, we consider the virtual strain now. So from the definition just now, du just now, Okay, the U just now from previous slide. So is equal to du is differential displacement, but this is real, u real. Okay, real. So this is equal to strain time dx. So this is just from last slide. If we consider strain is not real, so this is also real. This is real. But if this is not real, so the differential displacement virtual is d virtual u. So virtual u. So d virtual u is equal to virtual strain. We just replace virtual u to u here. So this is virtual u. This is not real. So we replace here u with virtual u. So we need to also replace strain E with virtual strain. Okay, so virtual strain times dx. Okay, so this is we call differential displacement virtual. Okay, so virtual U or virtual strain energy is equal to force. Force, this is sigma x times dy times dz, or this. Okay, so this is force times or multiplied to differential displacement virtual. So this is we take from this. Okay, so this is force. Force is real, and differential displacement is virtual. Okay, simply F is force times virtual. So this is become virtual d, d virtual u. Okay, so this is virtual, and this is incremental displacement in virtual. So F times d virtual u. Okay, so this is equal to sigma x. So we just move position virtual strain at here now. So now we collect all dx, dy, dz. So this is dv. Okay, the volume of this element. We need to take integral. Okay, we need to take integral. We need to take integral because this is just for one element, for a whole body, for a whole structure. So we need to integrate. So we need to plus energy, the virtual strain energy for one element. We need to sum all elements in the structure. So that's why we need to take integrate, or we need to consider integrate now. So this is for all element in the structure. So integrate, this is for element, for all element in the all elements in the structure, maybe bar or what, whatever structure. So this is why we use integrate here. Virtual U This is represent the virtual, the energy, the strain energy, and this is just virtual, not a real. Okay, so we simplify virtual U for the structure equal to integration sigma x times virtual strain times dV. Okay, so we consider the expression from last slide. Okay, so virtual work external is equal to virtual strain energy. So this is comes from last slide. Okay, this slide I just add in my Dropbox. You can refer back FEM underscore astronaut PDF file in my Dropbox. So I have add a few page. So let's refer back to my Dropbox and check this file. Okay, so we consider example now. Example is four determinate beam. This is just simple example. We consider a beam, simply supported beam. A we have pin support, and B we have roller support. Pin we have AX and AY represent the reaction, and at pin support or roller support here we have just BY, one reaction force. The dimension is as given, and W is applied load. Okay, use virtual work to calculate BY. Okay, we are going to use virtual work to calculate BY. Real forces are AX, AY, W, and BY. Okay, the simplest to find the simplest way to find the BY, we use total moment. This is equilibrium equation. Total moment at A equal to 0. Okay, so we take positive in this direction. So BY times L positive minus W times L1 equal to 0. Okay, so from here we get BY equal to W L1 per L. So I want to take the screenshot first. Okay, so BY is WL1 per L. So we are going to use a virtual work method to find reaction. So let's consider this is same beam. we impose a virtual rotation. This is beam, and this line. So this line represent the real deformed shape. We apply virtual, okay, virtual, but this is virtual rotation. This is just virtual, so this is beam, and this is virtual rotation. This is just imaginary, not a real one. This is also rigid body rotation. Okay, rigid body rotation, we have this is can rotate, and this is not involve strain, so no straining occur. So we assume that this is no strain. Okay, so no strain. Comes to this diagram again. Okay, and then we apply virtual work external equal to virtual strain energy. Okay, we apply this. Okay, so now virtual work external equal to virtual strain energy, but just now we consider no straining. Okay, so this is when this is rotate to here, so this is no straining to occur, so virtual strain energy is equal to 0. Okay, so the load, okay, so I need to take one more diagram. This. Okay, this is the diagram. This is a real diagram, real beam. Okay. This is real, and this is virtual. So this is virtual displacement. With the virtual work external. Okay, so we consider now the virtual work external is comes from work or load times displacement. So first come, this is we take a real one, W is a real, we multiply to virtual displacement or virtual UW. So this is virtual UW. The displacement or the virtual displacement at position of W. Okay, so W times virtual UW, we get this. And we put the minus because the direction is opposite. So W is downward, but virtual UW is upward. So minus sign because of W and virtual UW are in different direction. We find more load AY, for example, AY must multiply to 0 because this is no displacement. AX also multiply to 0, no displacement here, no virtual displacement here. But BY, so BY is a loading or real force, so we need to multiply to virtual UB. So this is virtual UB. So BY times virtual UB. And this is equal to 0. From similar triangle, from similar triangle, virtual UW per L1. For L1, we consider this triangle. We consider this triangle right now. So virtual UW per L1 equal to, now we consider the big triangle here. So from big triangle, so this is virtual UP per L. Per L. So from here we found that virtual UW is equal to L1 per L virtual UP. So virtual UW here is virtual UW here is equal to L1 per L times virtual UP. So we substitute from here. So this we substitute to here. We substitute to here. So this become virtual W times L1 per L. L1 per L. Virtual UP. So after we substitute here, we get this plus BY, this term, times virtual UP. Virtual UP equal to 0. So then we can factor. We can factor virtual UP here. So we can collect virtual UP and then we can factor. So finally, we because of virtual UP is non-zero, because this is non-zero, then we found that BY equal to plus WL1 per L. So this is comes from here. We found BY equal to WL1 per L. Because this is positive, this is upward. This is upward. So this is how we can find the reaction using virtual work method. So if we compare to just now, we use the reaction, we use the equilibrium equation. We found that this is By comes from virtual work method, and from equilibrium equation we found that this is the same. WL1 per L. So this is same, exactly the same. We consider a bar now. We apply the virtual work. The bar is subjected to member force F1 and F2. So this is we call N forces, and we have a point load W. So the point load W here we call as a member load. We apply virtual external work or external virtual work equal to virtual strain energy. The bar is displaced U1 here, so this is virtual U1 at left hand, and at right hand here the bar is displaced virtual U2. At point W, or the point load is acted at this point, so the virtual displacement is virtual U function of L1. Okay, so we apply virtual work external equal to virtual strain energy. Okay, so F1 first comes from F1 times virtual U1. So this plus F2 times virtual U2. So this is virtual work. This is external. Okay, so this is external virtual work. So F2 times virtual U2. And plus W. Okay, W times virtual U function of L1. We put minus here because the direction W and the direction of virtual U of L1 is in opposite direction. So this is minus. So equal to, from previous slide, the virtual strain energy is virtual strain time stress X time dV, and we integrate. Okay, so now we consider virtual U L1. We consider this term. Okay, we consider this term now. So virtual U L1 equal to this from previous slide, the function U X is equal to, and this is shape function, and 1 X and 2 X. This is shape function, row vector multiplied to U1, and this is nodal displacement U1, U2. Okay, so we apply here. Okay, we apply here. So if we have virtual, we consider virtual. So now this is virtual, and this is also virtual, virtual and 2. Sorry. So this is virtual N1 and N1 and 2 U1 U2. So this is, we put virtual here. So from here, if x equal to L1, so virtual U L1 equal to virtual N1 of L and 2 of L1, of L1, U1, U2. And we put the virtual U1 here. So virtual U1 and virtual U2. This is we have no virtual for N1 and N2. N2 and N1 L1 and N2 L1 all are shape function. Okay, so the virtual this become a virtual U1 and virtual U2. Okay, in the next slide, we consider again this term. Okay, we consider again this term and we substitute. Okay, we substitute from we substitute virtual U L1 here. This is from last slide. We substitute to here. Okay, so we get this F1, F2. We form a matrix multiplication. This is row vector and this is column vector. So F1 times virtual U1 plus F2 times virtual U2 become this. So this minus W, so minus W, and we need to substitute this to this. So this become minus W N1 L1 and 2 L2 virtual U1 virtual U2, so equal to this virtual string times sigma x. dv is a dx, so x varies from 0 to L. So the bar element just now, this is x equal to 0 and this is x equal to L. But this is from previous slide. Virtual U string equal to derivative of shape function times virtual U. Okay, so virtual string equal to d virtual U per dx. So virtual U okay, so this is d dx, so this is d dx. Virtual U is N1 N2 virtual U1 virtual U2. So the derivative of N1 N2 is here. This is N1 prime and N2 prime. So multiply to virtual U1 virtual U2. Okay, so this also from previous slide. We just multiplied to E. So this is real stress. Stress is E times strain, and this is E. The strain is derivative of shape function times U1, U2. U1 and U2 here are real. So we substitute now. Okay, so before we substitute, we need to expand this. Okay, so yeah, we have same column vector here, virtual U1 and virtual U2, so we can collect. So after we collect this, okay, we collect and we can factor. So this minus to this, because the vector is the same, we can just minus F1 and WN1 L1 here. Okay, so this is second F2 minus N2, or F2 minus WN2 of L1. Okay, so consider the right hand side of this equation. This is 0 to L, virtual strain here. So virtual strain is N1 prime, N2 prime, virtual U1, virtual U2. We substitute. Okay, so we substitute this to this. Okay, we substitute and we found this. Okay, this also the stress term here, we substitute to this. So we found this. Okay, so in the next slide, we transfer. We transfer we can change from here. We can change the position here. Okay, so this is a row vector and this is the column vector. We can change the position here. So virtual U1 become this, and we put F1 minus WN1 of L1, we put it here. And this also can change. Okay, this is can change WN2 of L1 and virtual U2. So we put virtual U2 right here, and we change the position WN2 L1 here. So this is F2 minus WN2 of L1. So equal to 0L. The virtual term here we can also change. virtual U1 we put it here, and N1 prime we put it here, virtual U2 we put here, and N2 we replace here. So this is change. After change take place, the position, change of position, because from previous slide, if A is a row vector and B is a column vector, so this is same as B. We change to a row vector, from column to row vector, and multiply to A. So you can refer back to previous slide. Okay, so after change position take place, we found here, and this we does not change. So this is maintained, this term maintained, so this is maintained. And this is A dx. Okay, so in the next term or next expression, so this is maintained the same, this is maintained the same, but here virtual U1 and virtual U2 all are virtual nodal displacement, so we can put it out of this integral, because both virtual U1 and virtual U2 are not function of x, because we integrate here based on x, so it came out of this integral. So 0 L N1 N2 prime E N1 prime N2 prime A dx, and this is also not function of x. This is nodal displacement, so we can put it out, so become this. Okay, so if we see this expression, now we have the virtual term at left hand side here at equation. Left hand side of this equation, we have virtual U1 and virtual U2 row vector, and at right hand side of this equation, we have virtual U1 and virtual U2. So finally we can cancel this term. So here we have no more virtual U1 and virtual U2. So after we cancel, we get this. And after that, we separate F1, F2, and Wn1, L1, and Wn2, L1. So this term comes from member forces just now. So after that, we get this F1, F2, and this we transfer to right hand side. So become this, and this is, we need to maintain this term. And finally, we simplify. The equation now become, this is Q, this is Q, this is N forces, N member force, and this is U, this is nodal displacement, this is U of 2 times 1, and here this is stiffness. So this is stiffness matrix, or member stiffness matrix K. So Q equal to KU, and this term is a member force vector. So this is W times N1 and the vector N1 and N2. So this is we call QF. So basically, the finite element is the same like stiffness method before. There is Q equal to KU, and then we need to plus to QF. So QF is a member force vector. Okay, next in the next slide, after the expression for N1 and N2, you can refer back to previous slide. So this is N1 of X is equal to 1 minus X per L, and 2 of X is X per L. And the differentiate of N1 is this, minus 1 per L. The differentiate of N2 is this. So now we can, the QF term here, so this is QF term, is equal to this, W N1 N2 and N2. So W times vector N1 of L1 and 2 of L1. So we need to substitute this. Okay, we need to substitute to this. So this is N1, and the N2 here, we need to substitute to this. Okay, so finally we get W N1 of L1 become 1 minus X is at L1. So this is 1 minus L1 per L. So this is N2 per L1. So N2 per L1 is this, X per L. So X is equal to L1. So this become L1 per L. Okay, so W, so this is equal to W L minus L1, and this is L1 L. So finally we get W L minus L1 is L2. So L2 per L, L1 per L. So this represents the member force. Okay, we can simplify from here. If the bar is fixed, okay, if the bar is fixed, this term represent the reaction. The bar is fixed and is subjected to W just now. So this represent the reaction of fixed bar. So the reaction here at this point is W L2 per L, and the reaction here is WL1 per L, the reaction here. So if we refer back to the stiffness method before, we have same expression like this, Q equal to KU plus QF. For example, if we consider beam, So the same equation can still apply. Q equal to KU plus QF, but QF for beam, we take the fixed and moment. Okay, for example, if we have a beam before, so this is fixed, and we have a distributed load. So still we have Q for Q equal to, for this member 1, so this is, we use Q, short Q before, so this is KD, and plus this is KD. So Q here, we take from this, we simplify the beam as fixed first, okay, and then after that we find the reaction. This is reaction from fixed and beam. Then after that we transfer to here. This is become nodal load. So this also transfer here become nodal load, but we take opposite direction. So the opposite direction is if we expand this, so this is okay, excuse me. So this become Q minus QF equal to KU. So this minus means we need to take opposite direction from fixed reaction to transfer to nodal force. That's why in the stiffness method before, we take opposite direction for member of fixed end moment to transfer to nodal, to node. Okay, so one more thing is to find K. So how to find K? K is a stiffness matrix of this bar. We can find it by using this equation. Okay, so by using this equation, we can find K, because all this is K matrix. We still use this. Okay, I need to take a new screenshot here. This is N1 and this is N2. This is from last or previous slide. Okay, so go to next slide. This is how to find K. So K is equal to this term. This is K. This is K. So this is 0L. So this is K. 0, we integrate from 0 to L. So N1 prime and N2 prime is given here. So this is N1 prime and this is N2 prime. We substitute to here. And then after that we found this minus 1 per L, 1 per L, multiplied to E, So N1 prime and N2 prime we take also from here. So this is N1 prime and this is N2 prime. So become this. So multiplied to A dx. So after we integrate, so this is E, so this is 1 per, we do multiplication first. This minus 1 per L times minus 1 per L, we get this, and this multiplied to this, we get this. This multiplied this, we get this, and this multiplied this, we get this. Okay, so we have no x function here, no x function, so we can move out from this integral. Okay, this, and then 0 L here, the integral is here now, 0 L a dx. So this is a dx, a time dx is al. Okay, so this term, this is 0 L a, we can put it here, so this is dx. Okay, so the integration is a 1 dx. So 1 dx integrate of 1 is x 0 L. So a L minus 0 is L. So that's why we get this AL. Okay, so this is AL. And after that, AL we multiply to E. Okay, AL multiplied to E and divide to all L square. So finally we get EA per L. So this is matrix 1 minus 1 minus 1 1. So this is same like truss before, truss stiffness matrix. So in the finite element method, we can find K by using virtual displacement method. Okay, virtual displacement method. We can find K and expression. This is basic expression in finite element method. So finite element method, finally we get this expression. So this is K. This is K. Okay, so this is K for truss. For other application, for example, beam, plane stress, or anything 2D problem with a different element, for example, triangular element before quadrilateral element, we can find K also by using virtual displacement method. But I just show you to find this equation for bar element only. But basically, the application of virtual work method can also apply to other type of element. For example, triangular element and rectangular element before. Okay, I think that's all my video. I think finish finite element method for this course, but you need to refer to or read the example. The example of finite element method, you can read yourself. I will put it in my e-learning. The example you can see. You can read and you need to understand when you read. Okay, that's all my video. See you in the next topic. Okay, assalamualaikum and have a nice day. Goodbye, everyone.